Let's talk about climate change. So the scientific evidence that climate change is happening, that it's human caused, and that we have to act today to avoid its worst impacts is overwhelming. Yet current policies and actions fall far short of what the science says needs to happen for us to continue to live safely on this planet. So today we're going to talk about that gap between what the science says needs to happen and current actions and how we can close that gap. So this chart here, it depicts that gap. It shows what historical greenhouse gas emissions have been in our atmosphere and what they might be under different scenarios, including the associated warming that we are going to experience. So the orange band at the top, it represents warming that we would experience if we adhere to the current climate-related policies that various governments across the world already have in place domestically. The blue band represents warming that would happen if countries adhere to their targets under the international climate pledges under the UN, under the Paris Accords. So you can already see that there's a gap between what countries currently have in place domestically and what they've said at the global forum that they're going to do. And then the green band at the bottom is what scientists say we have to aim for in order to avoid the worst impacts of climate change. And that's limiting warming to 1.5 degrees Celsius relative to pre-industrial times. So it's a really steep departure between kind of current greenhouse gas trends. The gap between what we need to achieve and the current policies and pledges in place is really the climate challenge that we're faced with addressing today. So big challenge that we're faced with today, and there's the ambition gap. So I want to talk about a framework today throughout the entire lecture for solving complex science-based challenges like climate change. So to solve these types of challenges, you really need three different components. One is the science. You need a clear understanding of the causes and the impacts of the problem. The second is solutions. You need viable technical and policy solutions to solve the problem that you've identified. And finally, you need the social will. You need support by people and politicians to address the problem and actually implement the solutions. So for climate change, like we've talked about, the science is settled. We know that climate change is happening, that it's human caused, and we have to act today to avoid its worst impacts. On solutions, maybe 15 years ago, the technology solutions weren't necessarily as economically viable or available to solve the problem. For example, 15 years ago, solar energy and lithium-ion batteries were more expensive, right? And either less efficient or more energy dense. And coal was a much bigger part of our energy mix. But today, since then, we've seen lots of innovation and cost declines in solar batteries, other clean energy technologies, to the point where we have economically viable solutions to decarbonize, in particular, our electricity mix and our transportation mix. And perhaps we need to innovate in a few smaller, hard-to-abate areas like industrial process heat or carbon capture, but really we need to focus on scaling already viable technology solutions like energy efficiency, wind, solar, and battery energy storage and electric vehicles. And we'll talk more a little bit later about frameworks for cost-effective, how we scale those cost-effective technology solutions. So we've got the science, we've got the solutions, but what's missing, and the reason why we haven't solved that the problem of climate change today, is the lack of social will. Our ability as a society, both in the US and globally, to accept the science and agree on appropriate action on climate change has been limited and intermittent. So in the remainder of this presentation, I'm going to walk us through this framework. We're going to talk about the science, we're going to talk about the social will, and then we'll end by talking about solutions. All right, so let's start with the science of climate change and what are the causes and the impacts. Our Earth's temperature is governed by what's known as the greenhouse effect, where greenhouse gases, they occur naturally in our atmosphere and they play a really important role in regulating Earth's temperature. In short, the way that it works, when sunlight enters the Earth's atmosphere, a portion of it is reflected back out into space, but another portion is absorbed by the Earth and re-radiated as heat. And greenhouse gases are heat-trapping gases, so they trap that heat and then keep the Earth warm. So greenhouse gases are heat-trapping gases, and as they increase in our atmosphere, so does our Earth's temperature. And we've known this since the early 1900s, if not before. We can see in this chart what concentrations of the most prevalent greenhouse gas, CO2, have been looking back hundreds of thousands of years, using data from ice cores in the Arctic and the Antarctic. But more recently, Charles David Keeling at the Mauna Loa Observatory began measuring CO2 levels directly since 1958. He passed away recently, but his son's continuing that work. And this is what's known as the Keeling curve. You can look it up online and look at it under different time frames. All right, so what you can see is that for the past 800,000 years, CO2 levels have largely fluctuated between 180 parts per million and 280 parts per million. But you can see at the end of the graph more recently, it looks like the border of the graph, but really it's just this crazy increase in CO2 getting us to where we are at today at over 420 parts per million, which is a significant and steep increase and a huge deviation from hundreds of thousands of years prior. And it tracks with the increase in carbon-intensive human activity since the Industrial Revolution. One thing to note is that CO2, greenhouse gases like CO2 are well-mixed gases. So when you measure them in one part of the world, like Charles David Keeling has done in the Mauna Loa Observatory, it's fairly representative of CO2 levels everywhere. And we'll talk about this more later, but this means that CO2 emissions from the US or China affect countries everywhere and is the reason why we really need to garner collective action on climate change. All right, let's talk about the different types of greenhouse gases. As I mentioned, carbon dioxide or CO2 is the most prevalent greenhouse gas and it's responsible for the most warming. But you've also got methane, nitrous oxide, and fluorinated gases. These are anthropogenic. These are human-caused. So methane has several sources. You'll learn more in the natural gas lecture. That includes natural gas for energy, but also methane emissions from landfills and livestock. Nitrous oxide, don't confuse it with nitrogen dioxide. Nitrous oxide comes from agricultural soil management, like fertilizers. And then we've got the fluorinated gases that are man-made gases, and they're often used as a substitute for ozone-depleting substances. So each of these gases have different heat trapping potentials and lifespans. So in order to understand the level of greenhouse gases in our atmosphere and create charts like these, we normalize them based on their heat trapping potential and their lifespan. And we normalize them relative to CO2. So using a metric called global warming potentials, or GWPs. So GWP, it's a measure of how much heat trapping potential a greenhouse gas has relative to CO2 within a given time frame. So this is why we often see greenhouse gas emissions measured in what's called CO2 equivalencies, or CO2e or EQ, like you see here in this chart. So when you see that metric, you know that those greenhouse gases have been normalized to each other based on heat trapping potential and time. So the table on the right up here, it shows international standards for global warming potentials for different types of greenhouse gases. Carbon dioxide is a very long-lived gas and can stay in our atmosphere for over 100 years, but methane has a shorter lifespan, only about 12 years. But methane has a much higher heat trapping potential than CO2. So you can see that using global warming potentials over a 20-year period, methane is about 80 times more potent of a greenhouse gas than CO2. If you look at it at a 100-year time frame, because methane has a shorter time period, that global warming potential is lower, 27 times than CO2. And you can see fluorinated gases have very high global warming potentials, but they're a relatively small portion of emissions, which is why you see them as only 3% there. So a lot of the data that I show you from the US in particular comes from the US Environmental Protection Agency's greenhouse gas emissions inventory that they release annually. And it's important to understand when you're looking at data like this, macro level data, to understand the methodologies. What are the emissions factors they're using that they're applying to activity levels that they understand are happening in the country. But in this case, it's good to understand that they use 100-year global warming potentials, which significantly affects the way that, say, methane shows up in these charts. But do we care about what happens 100 years from now? I think we care a little bit more about what happens in the next 20 years, right? Because we're seeing climate change happening now, and we're seeing those impacts happening now. So the EPA GHG inventory, among other things, is criticized for using those 100-year global warming potentials rather than the 20-year ones. All right, we've got black carbon listed at the bottom here. Black carbon isn't actually a greenhouse gas. It's actually the biggest light trapping component of particulate matter. We'll talk more about particulate matter next Friday. But it does have, significant heat trapping potential. It's also very short-lived, and it's unlike greenhouse gases, they're fairly localized. But sometimes you'll hear scientists talk about how, if we address black carbon in the atmosphere, that can achieve immediate warming reductions in kind of a low-hanging fruit type of way. Okay, so let's look at the sources of greenhouse gas emissions. So here you can see global anthropogenic, that's human-caused, greenhouse gas emissions. And you can see that they originate from a variety of different sources, right? Electricity, transportation, agriculture, forestry. But you can slice and dice this in different ways. If you look at sources based on our energy use, energy is the #1 contributor to greenhouse gases around the world, making up about a little over three quarters. So the energy resources that we have historically used to fuel our cars, to keep our lights on, they've predominantly been very carbon intensive. And this is why climate change and carbon intensity is such an important factor when we're talking about energy resources and our energy systems. So the result of the recent increase in global greenhouse gas emissions is that the Earth is experiencing a changing climate at unprecedented levels and speeds, with significant impacts already being felt by humans today. So let's talk about those impacts. And I want to call out that much of the data that I'm going to show you about climate science and impacts comes from the Intergovernmental Panel on Climate Change, which is an international body that's known as the IPCC, established by the United Nations of over 1,000 scientists across the world. And it's really considered the ultimate authority on climate science. So according to the IPCC, since pre-industrial times, global average surface temperatures have increased almost 2 degrees Fahrenheit or 1.1 degrees Celsius. So this is just another kind of visually, hopefully engaging way to show the temperature increases that we've seen across the world. Pretty striking. We talked about wildfires and wildfire smoke and people being displaced, their homes being burned down, both in the western U.S. and Canada, in Brazil and elsewhere. We already talked about rising temperatures at the surface level, but rising temperatures as well of the ocean impact the health of corals and other sea life and have resulted in increasing mass bleaching events for many of our coral reefs across the world. We've also seen increased melting of sea ice as a result of temperature increases in the Arctic and the Antarctic at really unprecedented rates, and a real kind of event that drove that home for a lot of folks is in March 2022, Antarctica experienced a record heat wave with temperatures jumping about 70 degrees Fahrenheit above normal. And the heat is likely what triggered the collapse of the Congar ice shelf that you see some images of here, which historically scientists thought was fairly well protected and fairly stable. So it came as a huge surprise. We've also seen sea level rise nearly a foot due to the loss of land-based ice and the thermal expansion of the ocean. And while it may be hard to connect what's happening in Antarctica or the Arctic with individual people, that huge loss of land-based ice results in sea level rise and flooding or coastal erosion for many populations that live in low-lying areas, everywhere from Alaska to Florida to the low-lying areas of the Bay Area to the island nation of the Maldives that you can see here. So, island nations, there are several island nations that have to actively talk about how to move entire populations. All right, and as we heard earlier, you've got, temperature rise means that the atmosphere can hold more water and result in really significant flooding events like we saw in Pakistan in 2022. We've also seen an increase in the severity of extreme weather events ranging from droughts and heat waves to hurricanes. Okay, so we also have, when we talk about impacts of climate change, we have what are called feedback loops that and positive feedback loops in particular, where increases in temperature result in further increases in temperature or greenhouse gas emissions. So to give a couple of examples, you've got the permafrost in the Arctic Circle, which is this frozen layer of soil and rock that naturally contains methane. And so as Earth's temperature increases, and when we talk about temperature increases, we talk about averages, but often those temperature increases are more extreme at the poles, like we talked about with the Antarctic heat wave and the Congar ice shelf collapse in 2022. But as temperatures increase, then that frozen layer of soil and rock called the permafrost thaws and releases significant amounts of CH4 and CO2, that methane and carbon dioxide. So that's an example of a positive feedback loop. Another one is the Earth's, we're talking about this here. That's an example of the methane and the permafrost being lit on fire. Another example of a positive feedback loop is, as temperatures rise and ice melts, that results in a reduction of what's called the Earth's ice albedo, because ice reflects sunlight rather than absorbing it and re-radiating it as heat. The more ice we have, the more of that sunlight gets reflected out, the less warming we have. So Earth has an albedo of about 30%. That means 30% of light gets reflected out that enters the atmosphere. And obviously that decreases as we get less ice. Any other positive feedback loops folks know of that they want to mention or can think of? A common one that people talk about is, with rising temperatures that results in rising air conditioning demand, and if that air conditioning demand is met by carbon-intensive energy sources, then that increases greenhouse gas emissions. Also, increasing wildfires, right? When you burn those, when those trees and vegetation get burned, that also releases CO2. All right, so positive feedback loops, they're complex, they're kind of hard to predict sometimes. They often have what are called tipping points, and there's been a lot of modeling around them, but good to be aware of them. Okay, so that's the science. So let's talk about garnering the social will to act on climate change. So as we've talked about, the scientific consensus that climate change is happening and that it's human caused is overwhelming. You rarely see issues have this level of consensus in the scientific community. The American public, however, differs quite starkly from the scientific community. And there are a variety of different reasons why that's the case, why it's so hard for the public to accept climate science, many of which relate to fundamental human biases that impact our ability to perceive risks and act on them. For example, climate change, it's a really big and scary and overwhelming issue. Often when people learn about the scale of the challenge, they feel helpless. So what the climate community has realized over time is that it's really important to not necessarily focus on the problems and the impacts that are scary, but talk about the solutions and how people can feel empowered to act on those solutions. So bear with me, we're going to get to the solutions in a moment. Another human bias that makes it challenging for us to act on climate change is our fight or flight bias. We're evolutionarily hardwired to respond to immediate threats in the short term. For example, if you see a lion, you run. We tend to discount future risks, and that means that we're procrastinators by nature. So long-term issues like climate change are much harder for humans to grasp and act on, particularly if there are perceived short-term costs to that action. The nature of climate change also makes it really hard for us to internalize because the issue is really hard to visualize, and the feedback between our actions and climate impacts are often diffuse, occurring over really long timescales. And sometimes, I used to say occurring over long distances in geography, but over time, as climate change impacts have accelerated, I think, as we've talked about earlier, almost everyone can point to direct impacts of climate change that they or their families have experienced. We also don't necessarily have the right people sending the right messages. Scientists in general don't do a lot of advocacy around their work, but the late Stephen Schneider, which you had an assigned video for today, who was a Stanford University professor and climate scientist, he was an exception to that. And he was actually criticized for promoting his scientific work and advocating for climate solutions. And because it was really something that scientists weren't supposed to do. But over time, as the social will has continued to be hard to garner for action on climate change, and climate impacts have accelerated, we really see the climate science community be much more vocal and take a much more active role in advocating for solutions. Communication on climate science has also been muddied by misinformation campaigns for decades, led by the fossil fuel industry, ExxonMobil chief among them, that actively funded organizations and scientists to sow doubt and uncertainty around climate science and its causes and impacts. But today we're seeing cities and states across the US sue fossil fuel companies for these misinformation campaigns. And as a result, the real impacts that those misinformation campaigns have had on people through climate impacts. Another challenge is that climate change is a very politicized issue in the US. How people understand climate change is more based on personal values and whether they are Republican or Democrat, rather than based on an actual understanding of the science or evidence. And top governmental figures have not really provided a consistent message around climate science. And we saw that with the first Trump administration, and we're seeing that again with this current administration. So there's a whole field of behavioral psychology that studies why people react to climate science in the way that they do, and what communication techniques can be most effective in spurring people to act, particularly in the right way. The Yale Project on Climate Change Communication does a lot of great work in this area. They study US public opinion about climate change and have identified 6 segments of the population based on how they think about climate change. The people in one segment are dismissive about the issue and they don't believe it's happening. Others doubt that it's human caused. Others don't engage or think about it at all. Luckily, that's like the smallest segment of the population. A larger segment, just under 20%, they're cautious and haven't made up their mind about climate change. The biggest segment is the concerned. These make up about almost 30% of the population. They think climate change is happening, that it's human-caused, and that it's a threat. But they support climate policies generally, but they don't necessarily think that climate issues are immediate, and therefore they deprioritize it relative to other issues like economic issues. And then you've got the second biggest segment, that's the alarmed. They're convinced that global warming is happening, that it's human-caused and an urgent threat, and they strongly support action to address climate change. So, although a lot of conversation might be focused on this portion of the population, the biggest by far are these two, right? So you can imagine that very effective climate change communications could focus on empowering the alarmed with concrete solutions and actions that they can take to address climate change. And the concerned, they just need to get communications that internalize the risks of climate change for them, right? Showing them how it's affecting them today and why they should prioritize it. And you can see why we might have this big disconnect, this big portion of the population that's in the concerned segment in the US. We've got 63% of adults who believe that global warming is harming people in the US today, but only 45% of adults believe that climate change is impacting them personally. So a lot of climate communications have focused on connecting extreme weather events or other climate impacts directly with climate change that are impacting individuals across the US. Another striking thing for me is that 64% of adults never discuss global warming, never or rarely discuss global warming. And that's something that I take for granted, right? In my work and here at Stanford, climate conversations are happening all the time. I talk about it with my family, my friends, I talk about it with my colleagues on a regular basis, but it's a conversation that's not happening in most of the US. And that's one of the reasons why I get really excited about education campaigns that help educate folks about, particularly in the K through 12 space, about climate change. All right, so we talked about some of the human biases and behavioral biases that are one reason why social will is so hard to garner for climate change, social will to act. A second reason why it's so hard is because of the equity issues surrounding climate change. The carbon budget, it's limited, right? It's what's called a common good. And we've got a tragedy of the commons here, which we'll talk more about next Friday, where scientists have said we need to limit greenhouse gas emissions to 1.5 degrees Celsius, to keep warming below 1.5 degrees Celsius, to avoid the worst impacts of climate change. So we have this limited carbon budget, and without regulation or cooperation, we're going to completely deplete that carbon budget and have a tragedy of the commons. I couldn't find a better, most up-to-date graphic, but here's 1.5 degrees C. This is where we are today. So the stakeholders involved in this tragedy of the commons are about 200 countries with varying levels of contributions to the problem and also differing levels of ability to adapt to the problem. So a lot of discussions in the international negotiations around climate action between countries have been around who has responsibility to act. So if you look at greenhouse gas emissions just annually, in the most recent year, you might conclude that clearly China has the most responsibility to act, right? They have the most annual greenhouse gas emissions. They're the biggest emitter today. But what are some other ways that we could allocate responsibility in the carbon budget?
Is the economic demand on China from other countries one of the reasons that China has the largest CO2 emissions?
Yeah, that's a great point. Well, I don't talk about that too much in this lecture, but there is a chart in the appendix that shows that kind of emissions shifting based on the emissions of what gets imported into a country, the upstream emissions. It's a really great point.
How do they measure the CO2 emissions a country produces? Do countries report their own?
Yeah, so under the UNFCCC, the UN climate negotiations, countries report annually on their emissions. And so it is kind of this self-reporting process, but there are a lot of efforts to verify that and check it, including by doing like satellite level emissions measurement. of methane and other types of emissions. But yeah, it is self-reported. So, gets back to the point of it's important to understand the sources of the data that you're looking at. I'll talk a little bit more about how it is what's known in economic game theory as a prisoner's dilemma, right? Where unilateral action just doesn't make sense rationally for any individual player or country to take action without action being taken by others, because CO2 is a well-mixed gas. So even if, say, India or China unilaterally reined in emissions, other countries would still be emitting and climate change would still be happening. But we have a better outcome if all the countries cooperated together to reduce emissions. Everyone's better off, right? So overcoming that prisoner's dilemma and garnering that collective action is very important, but challenging. Yeah, so you guys touched on some of the big ones. I think outsourced emissions is a really good one, not up here, but we should add it. CO2 per capita is a really important metric to look at. But other metrics to look at include cumulative CO2 emissions. We talked about that CO2 can stay in the atmosphere for over 100 years. So not just looking at annual emissions, but what historical emissions have been. You've got CO2 per unit of gross domestic product, so normalizing CO2 emissions based on economic development and the economy is important. That's also a metric known as carbon intensity. Another way of looking at economic and human development, other than GDP, is the Human Development Index, or HDI, which also looks at things like education and health within a country. And then you've got CO2 per total primary energy supply. So lots of different ways to look at CO2 emissions by country. So if you look at CO2 emissions based on per capita, earlier we saw that China is the largest kind of absolute greenhouse gas emissions emitter on an annual basis, but per capita, Australia, Canada, the US, and Russia top the list here. And then if you look at cumulative emissions, the US and the EU by far are the biggest emitters. But if you're looking at where the biggest increases in CO2 emissions are happening, that's really in the developing world. China and India in particular account for the bulk of increases in greenhouse gas emissions that we're seeing today and that we're anticipated to see into the future. But a part of the challenge is that some countries, particularly in the developing world, they have significant portions of the population that don't have access to electricity or are less economically well off, right? So what right does the US and the EU have to tell these developing countries to rein in their emissions and potentially compromise their economic growth when the US and the EU have historically been the biggest emitters and been the biggest contributors to climate change in the first place? Moreover, the hardest hit countries and populations by climate change are the poorest populations of the world. Yet they have contributed the least to climate change in the first place. So another topic of conversation on the international climate negotiations is what responsibility do developed nations have to support the adaptation of vulnerable countries in adapting to climate change? So these really big questions related to equity and climate change have really made ambitious progress on climate change at the international level very challenging. All right, so finally we made it to solutions. Let's talk about solutions. Closing the emissions gap and solving climate change, it's a significant undertaking. There's no one silver bullet option. There's no app to solve climate change, right? We're going to need to pursue multiple different large-scale actions across the world in order to close this gap. And it calls not just for a continuation of what we're already seeing in low carbon solutions, but an acceleration of investments in those solutions. But it is achievable. It is both technically and economically feasible, and we've got the solutions at our fingertips. So before diving into what solutions frameworks look like, I think it's important that we revisit the sources of the problem to understand where we target our solutions, right? Because you can't manage what you can't measure. Measuring and understanding the source of the problem is a really important first step in solving it. So this, again, it shows the different sources of greenhouse gases on the left and some of the tools that we have to reduce greenhouse gases, the natural tools available to us like land sinks and ocean sinks that can absorb CO2 and reduce CO2 in the atmosphere. So this is, potentially one useful way to look at the sources, but you can slice and dice it in different ways. You can break electricity out into its different end-use sectors. You can break it down by country and then by end-use sector. And as we talked about earlier, it's important to understand that the data that you're looking at is only as good as its source. The information that we have on greenhouse gases at this level is self-reported by countries, but there are a lot of ongoing efforts, including by scientists here at Stanford, to do bottom-up direct measurement of those greenhouse gases, not just to help check what's being reported by countries, but also to help identify specific sources so that we can go and plug them, right, and address them. A lot of this macro level data is at the country level or at the kind of economic sector level, but there are also robust frameworks for measuring and accounting for emissions at the organization level or the business level. Stakeholders have created standardized reporting practices for companies and organizations to follow when measuring and accounting for emissions. And an important concept to understand in this endeavor is that of Scope 1, 2, and 3 emissions, which divides emissions based on the direct control that an entity has over those emissions. So Scope 1 includes direct emissions from company-owned equipment, like from company vehicles, or if they have, like a natural gas boiler. Scope 2 includes indirect emissions from electricity, heat, or steam that's purchased by a third party, like a utility. And Scope 3 includes all other indirect emissions that occur from a company's supply chain, such as the emissions associated with the manufacturing of goods bought by the company. Significant development in GHG reporting occurred in the US in 2022 when the Securities and Exchange Commission announced that they were going to require companies to report on these emissions. Because historically, prior to the SEC regulating this, public companies would often release greenhouse gas reports that show what their greenhouse gases were, but it wasn't necessarily anything that was if it was verified, it would be by like a nonprofit entity who was doing it or just voluntarily reported based on other non-mandatory standards. But now with the SEC regulating it, and they did end up putting in place regulations requiring public companies to disclose specifically Scope 1 and 2 emissions. They didn't require Scope 3. There was a lot of discussion and controversy over that. Creates a whole other level of robustness around what public companies are reporting. So that's about measuring. Let's talk about solutions frameworks. There are several great science-based frameworks available that outline pathways and cost-effective technical solutions that we can pursue and scale to meaningfully reduce our greenhouse gas emissions and stabilize them in our atmosphere and avoid the most dangerous impacts of climate change. This one is a summary project drawdown results that show that energy solutions are by far one of the biggest chunks of addressing climate change. In addition, a big portion is those carbon sinks, both natural and engineered, those so-called negative emissions that take carbon out of the atmosphere. Maybe 15 years ago, carbon sinks were a much smaller part of the solution and not really part of the discussion around solving climate change. I think in part because we hadn't emitted so many greenhouse gases in our atmosphere, so we had less of a need for them, but also because scientists and others didn't want society to think that we can engineer our way out of this problem, because doing so is going to be really hard. But as we've continued to emit more greenhouse gases over time, the importance of natural and engineered sinks have increased in these solutions frameworks. So they include increasing natural sinks like forests and regenerative agriculture, but also engineered sinks like directly capturing carbon from the atmosphere and putting it underground or repurposing it into other products. like bioplastics and fuels. I also just want to call out the education and health component of Project Drawdown Solutions Framework, which makes up about 5% of the solutions in the scenario on this slide. And Project Drawdown believes that family planning and universal education are essential human rights. And a result of that is a reduced population that results in less emissions as well. So I think it's interesting and important that Project Drawdown has included that in their framework. In addition to Project Drawdown, we've got the Exponential Roadmap that provides another solutions framework, published in 2019 by an international group of experts that included Rob Jackson, a Stanford professor. And it maps out 36 different cost-effective measures that we can take today to have emissions reduced by 50% by 2030. And you can see again that decarbonizing our energy mix, including in industry and buildings and transportation, is a really big part of the solution, as is specifically they focus on nature-based sinks. So what these frameworks are telling us is that really we just need to scale, focus on scaling these already available decarbonization solutions if we want to make a big dent in climate change. Let's dig into this concept of cost effectiveness. I've talked about in these solutions framework that these are cost-effective solutions, but what does that mean? Cost effectiveness is important, right? Because we're not going to see solutions scale if they aren't cost effective. That's just how our economy works. So this chart, it's from a seminal study published by McKinsey initially in 2010 and then republished in 2017. And although there's been technology innovation and changes in the economics since then, I think it's a really great way to think about cost effectiveness of different GHG abatement levels. So the x-axis, it shows CO2 abatement potential of different solutions and technologies. And the y-axis shows the cost per ton of CO2 abated. So all of the solutions on this side here that are below the x-axis, those are cost-effective solutions, right? They have negative costs, they're profitable, that we can take, many of which are energy efficiency measures. The cheapest and the cleanest kilowatt hour is the one that you don't use in the first place. For these other measures that are above the x-axis, like wind and solar, since this has been published, we've seen the costs of wind and solar come down even more precipitously to the point where in most of the world, wind and solar are actually the cheapest electricity resources that you can build today. And all of these solutions, they would be more cost effective if you price in the external cost of CO2. I believe you talked on Monday with Diana about externalities and how there's a difference between the private costs that we pay for a good or service and the social cost to society, and that difference is externalities. So the external cost of carbon is widely known as the social cost of carbon because someone in society is paying the price for the greenhouse gas emissions that we've emitted, right? And putting a price on carbon helps us ensure that polluters are the ones that pay it. And it sends the appropriate market signals to help reduce demand for carbon-intensive products and address that market inefficiency created by those externalities. So because of this, we've seen a lot of different countries put in place a price on carbon, both at the country level, but also at the state and local level as well. Like in California, in the Northeast, they've got their Regional Greenhouse Gas Initiative, RGGI, and elsewhere. And there are a couple different ways to put a price on carbon. The first is by governments mandating it through things like a carbon tax or cap and trade mechanism. The EU and California both have cap and trade mechanisms. RGGI is a cap and trade mechanism as well. That's kind of a market-based mechanism that was actually first used in the US in order to reduce NOx and SOx emissions that were causing acid rain. It was actually a mechanism that was proposed and advanced by Republicans because they liked it better than a carbon tax because it was a market-based mechanism. But has since become a lot more politicized in the context of climate change. The second method of putting a price on carbon is for stakeholders to do so voluntarily. And we see a lot of businesses, we've seen a lot of businesses voluntarily, like Microsoft and Google, put in place an internal price on carbon. So when they're doing analyses, cost-benefit analyses of different actions, they're taking into account the cost of carbon of that activity. But one of the biggest challenges to putting a price on carbon is, what price do you set it at, right? The EU's price on carbon, it might trade around $100 a ton. In California, it might be more so around $30 a ton. So you can see a pretty wide range of what those costs of carbon are. But if we go back, and there have been studies out of Stanford that show that the actual social cost of carbon that we should be using is around $200 a ton or more, based on the actual impact to society. We talked a little bit about the international climate negotiations earlier, but I want to dig into that more. So we talked about, because CO2 is a well-mixed gas, and because the carbon budget is a common good, a limited common good, we need collective global action on climate change, and that it's this prisoner's dilemma, right? Where individually countries aren't going to act alone as rational players, but if we all come together to coordinate, we're more likely to act together and result in better outcomes for all. So because of this, the world has been trying for decades to garner collective action on climate change. In 1992, parties to the United Nations signed an agreement called the United Nations Framework Convention on Climate Change, the UNFCCC, where they agreed to work together to help stabilize emissions to keep warming to safe levels. And there are nearly 200 countries that are signatories to the UNFCCC. One of the significant outcomes of the UNFCCC process is that in 1997, many parties to the UNFCCC adopted the Kyoto Protocol, which included legally binding greenhouse gas mitigation targets for developed countries only. The US didn't formally ratify the Kyoto Protocol for a couple of different stated reasons. One, they didn't like that developing countries didn't have any mitigation targets under the Kyoto Protocol. And second, they were afraid that it was going to be too costly for the US to comply. The irony is that ultimately, if the US had stayed in the Kyoto Protocol, they would have blown past their mitigation targets because of coal to gas switching and transportation efficiencies that happened during the Kyoto Protocol term. In the end, also several countries, such as Russia and Japan, ultimately missed their targets under the Kyoto Protocol. So the results of the Kyoto Protocol, as have the results of many attempts at international cooperation more broadly, have been mixed. Since the Kyoto Protocol, UNFCCC negotiations have largely been focused on developing a new agreement that includes mitigation targets from both the developed world and the developing world, particularly given that most of emissions increases are coming from the developing world. And so finally, in 2015, parties to the UNFCCC adopted the Paris Agreement that included just that, mitigation actions by both developed and developing countries. And as we talked about before, topics negotiated at these negotiations, which, the big COPs, the Conference of the Parties, they happen once a year in the November and December timeframe, but there are negotiations ongoing in the interim as well to try to advance. So it's not just like everyone coming together and hoping that they can get something done at the end of the year, although sometimes it does feel that way. But topics that are negotiated don't just include mitigation targets, they also include things like how the developed world can help developing countries both invest in climate solutions and adapt to climate change. Another thing to note about the UNFCCC process is that it relies on consensus, which means that any single country can raise their hand and stop action. Which can make it really challenging to advance progress. To give you a sense of how individual countries come to the table, you can imagine that the US has been limited in its ability to act internationally because we've struggled to have consistent domestic policies on climate change to support any pledges that we might bring to the table. And the current administration in the US is a really big determinant of how we show up in the international climate negotiations. For example, the Trump administration, I believe under both administrations, has pulled out of the Paris Agreement, or at least expressed their intent to do so. Then you've got China, where historically the country had prioritized economic growth over climate action and had held up the climate negotiations, saying that they didn't want to take any action if the US wasn't going to take action. But more recently, in the past several years, China has done a bit of a 180 and taken a much more of a leadership role in the international climate negotiations. And in part because, one, it has a desire to be a global leader on issues like these, but also domestic pollution relating to energy use and other carbon-intensive activities caused really severe health effects for its population, and so it just made a ton of sense for them to start taking climate action. And then you've got oil-producing countries like Saudi Arabia who delay action because they have obviously a very big vested interest in the world continuing to consume oil. And then, of course, you've got the less developed countries and small island developing states like the Maldives that are not huge contributors to climate change, but they're going to need to adapt to the increasing impacts like sea level rise and extreme weather. And to drive this home, President of the Maldives held an underwater meeting with his cabinet in 2009. So you can imagine that, if you're Saudi Arabia, you're going to try to raise your hand and say, I'm not supporting action on this as much as possible. If you're the Maldives, if you're not getting enough support that you need to adapt to climate change, you're also going to try to hold up negotiations until the world comes to its senses and provides the necessary support that they need. The ability to garner the social and collective will to act on climate change is really hard because of the difficulty in slicing and dicing who has responsibility to act. So because of these conflicting positions and the 200-player prisoners dilemma, often negotiations break down and devolve into smaller huddles. Like you see here, this is at COP16 in Cancun in 2010. I know these are a little bit old, but they're when I was part of the negotiations, and I just remember it being so interesting. COP17 in Durban. And these breakdown in negotiations, they ultimately lead to a watering down of the agreement and also to the targets that countries bring to the table. So the result is that we are left with this ambition gap, not only between the domestic policies and actions that countries currently have in place at the top and what they've pledged to the internationally in the Paris agreements, but what the science tells us needs to happen. Regardless of what's going on in the international climate negotiations, we're still seeing a lot of progress on climate solutions that happen domestically and in the private sector and private markets that I think help carry the momentum and carry the water in the absence of this collective action. So let's look at that and hopefully end on a note of optimism. For example, we've seen a decoupling of economic growth and CO2 emissions in several countries across the world, both developed countries and developing alike, which is a strong indicator that countries don't have to compromise their economic development in order to rein in emissions. And in fact, economic growth can be spurred by low carbon technologies. As we talked about, the most cost-competitive electricity resources that we can build today, even on an unsubsidized basis, are the cleanest, like renewable energy, energy efficiency, and electric vehicles. And because of this, wind and solar are actually the fastest growing energy resources worldwide. This is the chart. We'll dig into this more. It looks complicated, but you'll understand this like the back of your hand by the end of this class. The levelized cost of energy analysis, we use Lazard's that is released by that firm every year. But yeah, you'll know how to calculate this by the time the class is over. All right, and like we talked about, we're seeing significant growth in wind and solar and electric vehicles that have blown past projections. You've got solar capacity installation forecasts from the International Energy Association here, the IEA agency, excuse me, where you see that actual growth has been exponential, that black line, and in stark contrast to the IEA's forecasts. And similarly, on the right, you've got zero-emission vehicle forecasts from multiple different sources, Bloomberg, OPEC, IEA, all of whom are now forecasting that zero-emission vehicles are going to make up over 50% of sales by 2050, which is exciting. In the US, obviously we're faced with, since January, an administration change and shifting priorities. But there's still a huge impact that the prior administration has had with the passage of the Inflation Reduction Act and the bipartisan infrastructure law making historic investments in clean energy and climate solutions, with a priority focus on communities and ensuring that communities can participate in the low carbon transition, which is a level of investment we had never really seen before. And in part came out of the fact that at the national level, we have been very unsuccessful at passing climate policies like a carbon tax or a cap and trade mechanism. So in its place, what the IRA did was make significant investments directly into clean energy technologies and climate solutions. All right, and I do have a workshop, I think 3 Mondays from now, if anyone wants to join, where I'll talk about federal climate investments and what that's looking like on the ground, especially now. I said earlier, the Nevada Clean Energy Fund has secured $200 million in federal funds over the past several years, all of which are legally obligated, but that's not stopping the new administration from illegally trying to claw that back. We've got about $20 million of our funds for tribes that has been currently paused right now, and I have no idea why. No communication at all from EPA. And the result is, frankly, that the tribes that we're working with have had to pause procurements and investments and staffing capacity focused on infrastructure investments that they've been working on for over a decade. So pretty detrimental. I mean, whether or not you agree with the government's current administration's approach of, and priorities around government efficiencies, this is not necessarily the way to do it. So I want to talk a little bit about the role of green banks in advancing climate solutions. So green banks like the Nevada Clean Energy Fund are present across the US. You can see almost every state has a green bank. And even in the areas that are grayed out, there are regional and national green banks that serve those areas, and ongoing efforts to develop green banks. So these are entities at the state and local level that leverage a variety of different sources of funding, federal, private, public, philanthropic, in order to fill gaps in clean energy markets. And I think one of the things that you'll see, we saw this under the first Trump administration when priorities at the federal level shifted away from climate and clean energy. You'll see momentum continuing to move forward at the state and local level, whether you're talking about policies or acceleration of investments and scaling solutions by all of these amazing institutions that I work with on a regular basis. We're also seeing continued investments by the private sector, where we've seen shifts in where the markets are focused, with global investments in cleaner forms of energy rivaling global investments in traditional forms of energy. And of course, action continuing here at Stanford with priorities and momentum under the newly created Stanford Doerr School of Sustainability. All right, so let's end by talking about what you can do as an individual. As we talked about, you could focus on your own individual carbon footprint, but like we talked about with the international climate negotiations, that any one action of an individual alone can't really put a meaningful dent in climate change. So if you really want to meaningfully address climate change, I challenge you to take a step back and make the problem bigger and really look at the levers that you have available to you to have an impact, whether that be how you vote, how you engage with the corporations that you work for or that you buy products from, and how you engage socially and philanthropically. By taking this bigger approach, you can really look at ways that you can catalyze solutions beyond your own individual carbon footprint. So today, we know that we have to decarbonize our economy to live under safe conditions on this planet. The question that you have to grapple with is what role you want to play in the decarbonization of our economy. And never more than today is the role that you all are going to play important, given the lack of momentum at the federal level. Thank you.